Hello, my name is DeNicholas, and this is my presentation on leveraging machine learning for new redox active molecules such as phenothiazine. I first want to thank Dr. Pencer and Dr. Tabor for being great guides and resources throughout this research project and providing me with the necessary knowledge to succeed. I would also like to thank the Texas A&M OREU for the opportunity to have this experience. The overall purpose of this project is to streamline the process of creating redox flow batteries by making a tool that will predict the solubility of new redox active molecules. To do this, we had multiple goals and various methods of approaching them. We wanted to utilize machine learning to predict the Hansen solubility parameters for phenothiazine and its derivatives as seen in the images above. We also set out to validate the simulation of solubilities based on previously reported results and do so by applying Gaussian as a machine learning model. Gaussian would be useful for this project to create inputs for regression models. Lastly, we wanted to be able to use our DKit with Python to obtain molecule fingerprints, also to be used as input in the regression models. Before getting started on all of these goals, I had to learn how to navigate the high-performance research computing facility remotely. I applied for an account through the HPRC and watched several hours of tutorial videos on how to connect to the VPN and Terra cluster, along with learning how to navigate through directories and write job scripts in Linux. Needless to say, there was a huge learning curve. But by the start of the second week of the program, I was in and ready to start running calculations in Gaussian. I was able to utilize a website called Entos Envision to generate coordinate files for a base set of 20 solvents using their smiles, which were easily found using PubChem. All of the calculations were made using the initial conformer of each solvent. To the right, you can see an animated 3D model of acetone made in Entos, which was a molecule included in our solvent set. Finding smiles for phenothiazine and its derivatives was a bit more of a challenge, so I used another online resource called OpenBabel at cheminfo.org. Here I was able to draw the molecules and receive smiles directly from the drawings I was provided at the start of the project. I used these smiles to generate coordinate files in Entos that would later turn into my input file for Gaussian. This was the method I used to obtain Gaussian input for phenothiazine and all of the derivatives relevant to this project. Once I had all of the coordinate files for the solvent set, I was able to start running calculations in Gaussian. I originally used WB97XD as the level of theory for the calculations, but found that the results were not matching enough with the previously published data, so we decided to increase the level of theory and ran the calculations again using B3LYP. As part of the calculations, I was able to obtain the polarizability of all of the solvents in the base set using the Raman frequency calculations. I tried to obtain exact polarizability of phenothiazine derivatives and radical molecules using the same type of calculation, but I was not able to complete this due to time constraints and running into errors. But with the calculations being completed, it was time to start collecting data. The calculations produced a lot of data for the solvents, but not all of it was relevant to the project's goals. I scanned through the output files from Gaussian to find the dipole total, electronic spatial extent, polarizability, and the HOMO and LUMO. I compiled all of this data into a spreadsheet where I could calculate the HOMO-LUMO gap and compare the data to the previously recorded results. These results matched much closer to the data I was using for comparison, so we felt comfortable using it as input for the regression models. Now that I had all of the relevant data, I could begin constructing regression models. I started with making simple linear regressions by pairing calculated parameters with known Hansen solubility parameters for the solvent set. To the right, you can see the data did not fit a 2D linear regression model very well, but this was expected because there are many more predictors to consider for calculating the solubility parameters. The linear fit in this image shows a likely relationship, but the other linear 2D models did not have the same clarity. To attempt getting more robust regression models, I used a statistics software called Minitab, where I was able to make 3D surface plots of the data as well as generate regression equations. I used the HOMO-LUMO gap, dipole total, and electronic spatial extent calculated from Gaussian, along with the molar mass as continuous predictors, and the responses were the known Hansen solubility parameters. I was able to get a regression equation for each of the parameters. In the model summary, it is clear that this model has a better fit, with an R-squared value of almost 63%, compared to the 2D linear model that had an R-squared value of 40%. The surface plot of the polar solubility parameter versus the dipole total and electronic spatial extent shows that there is a likely relationship, but does not include the other predictors being considered for the regression model. With preliminary regression models being completed, I also set out to get the solvent molecules' fingerprints using RDKit and Python. Molecule fingerprints are a series of binary numbers associated with the molecule and are often used in the pharmaceutical industry. I was able to generate the molecule fingerprints by using RDKit in Python. I input the smiles for each solvent and received a vector array filled with ones and zeros for each molecule. The image on the far right shows a shortened version of the molecule fingerprints for phenothiazine, with an array filled with the location of ones in the larger binary array. Although the purpose for obtaining the molecule fingerprints was to use them as a categorical input for the regression models, I was not able to generate a model with them yet due to delays and complications with the RDKit package. Now that I had all of the relevant input data and some preliminary regression models, I could start calculating the Hansen solubility parameters for phenothiazine and its derivatives. The original regression equations had a fair fit, but I knew it could be better after normalizing the data and adding polarizability as a continuous predictor. In the model summaries for each parameter, it is clear that polarizability and normalizing the data had a major impact on the regression model. As previously stated, I was not able to get the polarizability for phenothiazine or its derivatives, so I would not be able to use it as an input for calculations at this time, but hope to return to this in the future when I have that data. I was able to run calculations for all of the phenothiazine derivatives included in this project and received results for the 3 Hansen solubility parameters. These values were calculated using the regression equations generated with not normalized data and excluding polarizability as a predictor, because at this time I don't have the proper data to run a more accurate calculation, but I hope to be able to do so in the near future. That being said, the consistency of these results is promising, and we hope to expand on this in the future, and hope this model can be used to predict solubility of other new redox active molecules. Thank you so much for watching.